Hi and welcome back to my video series on vectors and lines in Unit 3 Topic 2 of the Specialist Math Curriculum, and this is video 6 and in all likeliness my final video. It might be a little bit longer. It's going to have a bit of a review of a few of the things that we've done, introduced a few new things and take you through a couple of examples. And we'll probably look predominantly in three-dimensional space as well. So in this section we'll be exploring intersecting lines, skew lines, parallel lines, concurrence. We'll quickly revisit the angle between lines, but I'll just talk about that and I won't do an example on it. Hopefully you can pick one up and follow it. And we might also talk about planes that lines exist on and the idea of two lines being coplanar if they intersect. So for lines in three-dimensional space represented by vectors, we already know that they are parallel, and so I'll just, my apologies, there we go, slow on the OneNote there. They're parallel if these two vector representations of the lines have it such that the distance is a linear multiple of the other distance. So there's just a constant between them. And we'll actually have a look at a really simple method to test that, but there's going to be a lot of ways you can read about to test that, so we'll just go through the simple one. So they're parallel if the distances are parallel. They intersect if when you solve for your 1, 2, or even 3, if you're looking at concurrence parameters, when you solve for those in the I, J, and K dimensions, you get a solution and not a contradiction. And if they parallel and intersect, then they're called coincident. If you have a look at my little diagram here, I guess the point I'm trying to make is if we think about this, two lines are parallel if they run at the same direction and basically they don't meet. That's the idea. But two lines could be parallel if they're actually the same line because they're still running in the same direction. But in this case, they're parallel and they have at least one common point. It actually turns out they have an infinite number of common points, every point on their line. And that means they're the same line, which means they're coincident. So there's coincidence, parallel, and intersecting lines for you. To find where two lines meet, simply equate and solve for mu or sigma or lambda or t or whatever it is. So example 8, let's find a point of intersection of these two lines. So the first thing we're going to want to do is rewrite it in terms of the I component and the j component. This is two-dimensional. So R1 is equal to 2 plus lambda I, and then plus -1 plus lambda j. And R2 is equal to 3 plus mu I, and then minus mu j, because there's no other value there. And I'll just quickly create a bit more extra space for myself. I seem to have to do a lot. Now, if I look at the I components and equate the I components, and then look at the j components and equate those, for these two to intersect, there has to be a point in time where the two yellow bits are equal. And there has to be a point in time where the two green bits are equal. So we're going to solve these simultaneously to find that point in time, if indeed it exists. But it might not exist, although this is two dimensions, so unless they're parallel, it has to exist. So let's have a look. We've got 2 plus lambda is equal to 3 plus mu, and we've got -1 plus lambda is equal to negative mu. So this is equation 1, this is equation 2. We get two equations, two unknowns. So this is technically solvable, although it won't create a contradiction, but there might be infinite solutions. So to solve this, I'm going to take equation number 2 and recognize that it can be written as mu is equal to 1 minus lambda. I'm just multiplying everything by -1. And that gives me, in equation number 1, 2 plus lambda is equal to 3 plus 1 minus lambda. And that gives me 2 plus lambda is equal to 4 minus lambda, which gives me 2 lambda is equal to 2, and that is lambda equals 1. So that's my lambda value. And over here, mu is equal to 1 minus 1, which equals 0. And now all I need to do is determine the value of R1 or R2 based on our findings. And so just quickly, R1 of course is, well, I was trying to create space but I failed at that. 2 plus lambda is 3 I, and -1 plus lambda is 0j, so I just get 3i, and R2, if I put 0 in for mu, is just 3i as well, so 3i is the point of intersection. So there you have a way of finding the point of intersection, which we have seen before. This works in 2 dimensions and 3 dimensions. So here's some further notes. If there's a contradiction, so what I mean by that is if for some reason you get a lambda and a mu that are different for 2 different equations, then that means that they're parallel, or that perhaps they don't meet. So parallel in this case, but 3 dimensions, that means they don't meet. If there's a distinct solution as an intersection, there's no solution but no contradiction, then they're coincident. So that no solution will actually mean there's an infinite number of solutions. So for the contradiction, you'll get something like lambda equals 2 and lambda equals 4, or 2 equals 4, or something like that. And for the no solution, you'll get something like 7 equals 7, which will just seem a bit weird. Your lambdas and your mu's will cancel out. So in 3 dimensions, the results are very similar. There's just some slight variations, and that is, in 2 dimensions, 2 lines are either parallel or they cross, or they're coincident, which means they cross and they're parallel. In 3 dimensions, and just imagine you could pick up 2 rulers or 2 pens and try this, you'll see that you can have a situation where the lines don't intersect and they're not parallel. If you're holding 2 pens or even a knife and fork in your hand eating dinner, they won't be parallel, but one will be under the other. And I've tried to draw that representation where this is the closest distance, this dotted line between them, but L2 is going in a different direction to L1, but it's underneath L1. So you might have that situation as well. This is called a skew line. So if line 1 and line 2 are skew lines, then that means they don't meet and they're not parallel. So here's a summary of the ideas, and a bit more of a summary than earlier. And so I'll run through this very quickly. Parallel lines is if the direction is the same, and we get the situation where the direction vectors for each d1, d2 have to be linear multiples of each other. Intersecting lines, if you equate I, j, and k, then you should be able to solve for mu and lambda and get a distinct solution. Still one distinct solution. Otherwise, you've got coincident or parallel or skew lines. Coincident means that 1 and 2 are true, so they intersect at least one point and they're parallel. And concurrent lines is an additional thing here, which you might see pop up. Concurrent lines are if 3 or more lines meet at one point, which obviously you can prove just by finding the pairs of intersection. And of course, the angle between 2 lines can be calculated by doing cos theta equals d1 dot d2 or dot product d2 over the modulus of d1 times d2. So that's something that we learned in the first topic on vectors in Unit 1, and that we need to bring back here as it might come up again. And you'll notice here that I haven't put in a definition, or definition probably 5, it would have been of skew lines, but that comes up here. So skew lines are the situation where not parallel and don't meet, we create skew lines. So in example 9, which is the last one I'll do for this series of videos, determine if R1 and R2 given are parallel, they intersect, or they're skew, or they're coincident. And keep in mind, coincident means they're parallel and intersect, so don't just stop at parallel. Check if they see if they intersect as well, for example. So the first thing to do is test for parallel. And parallel will mean that D1 equals K D2. This is testing parallel. Now this is, I believe, is the easiest way of doing it. So D1 is equal to 2I plus 4J minus K, and D2 is equal to 5I minus 4J plus 4K. Now, what we mean by is a linear function is we consider, let's say K for example. To get from D1 to D2, negative K would have to be multiplied by negative 4 to get it to positive 4K. So this is saying that this has to be multiplied by negative 4, and D1 is equal to negative 4 D2. And negative 4 is that factor that creates the parallel lines. And that would essentially mean that D1 is this vector, and D2 is this vector, parallel to D1, but 4 times longer and in a negative direction. But that has to be true for all of them. That negative 4 has to be a factor of all of them. So once I've worked out one of them, negative k times negative 4 would give me plus 4k. Well, that should also be true for my j's. And of course, positive 4 times negative 4 will be equal to negative 16. So it actually falls over here. That straight away, it's not parallel. But we can take the test further and we get this 2 times what equals 5. It's certainly not negative 4. So we get an issue. The other common way of looking at it is just looking at the ratios. Basically, the ratio, the I ratio, which is 2 over 5 or 5 over 2, should be equal to 4 over negative 4, should be equal to negative 1 over 4, and that's not true. So these are not parallel. That's our first one. And if they're not parallel, it means that that's out, and it also means that coincident is out. So now it's either they intersect somewhere or they're skew lines. And we'll know once we test that intersect. So let's test the intersect by first representing R1 in I, J, and K notation with our lambda. So we get 3 plus 2 lambda I, and then we get negative 1 plus 4 lambda j, so I should put a little plus in here, and then we get plus negative 1 minus lambda k. I forget these little squiggly lines a lot too. And R2, which is also a vector, is 1 plus 5 mu I plus 2 minus 4 mu j plus, sorry, my apologies, minus 3, so actually we should have a plus there, plus negative 3 plus 4 mu k. Now, what's going to happen here is we're going to create 3 simultaneous equations. So we need to be able to show that 3 plus 2 lambda is equal to 1 plus 5 mu. So the I components must be equal. And of course, the second one will be negative 1 plus 4 lambda has to be equal to 2 minus 4 mu. And that is this one. And lastly, negative 1 minus lambda has to be equal to negative 3 plus 4 lambda. And now we're looking to see if we can solve this and find 1 lambda, 1 mu value, or will we reach a contradiction? If we can solve it, there's a point of intersection. If we can't solve it, then it's a skew line. So let's start by looking for the easiest way to isolate either lambda or mu. And I think really if I call these equation 1, 2, and 3, the easiest way is really in number 3. So in number 3, I can get negative lambda is equal to, I add 1 to both sides, so negative 2 plus 4 mu, and that gives me lambda is equal to 2 minus 4 mu. So there's my substitution, and I can substitute that into number 1 to start with, and I get 3 plus 2 times 2 minus 4 mu is equal to 1 plus 5 mu. And so that gives me 3 plus 4 minus 8 mu equals 1 plus 5 mu. Getting all my mu's on one side and all my numbers on the other, I'll move the 8 mu across so that I keep the mu's positive. So I'm adding 8 mu, subtracting 1. 3 plus 4 is 7, minus 1 is 6, equals 13 mu. And so therefore mu is equal to 6 on 13. And to be honest, with my experience, I generally know now that if mu is a really weird number, it's really unlikely for 6 over 13 to come up in the next one. It's quite hard to set a question like that. So in the second one, I get negative 1 plus 4 times lambda, which is 2 minus 4 mu. And that has to be equal to 2 minus 4 mu. And so I get negative 1 plus 8 minus 16 mu equals 2 minus 4 mu. And now I'm going to put, again, the mu's and the numbers together. So I'll add 16 mu to both sides, subtract 2. Negative 1 plus 8 is 7, minus 2 is 5, and negative 4 mu plus 16 mu is equal to 12 mu, and I get mu is equal to 5 on 12. which is actually not that far away from 6 on 13, but a contradiction nonetheless. They are not the same number. Therefore, this is showing that mu is two different things to make these work, which implies that mu is neither of those things, and there is no possible mu to make this work, and therefore there's no possible lambda, and therefore we have skew lines, not parallel, and they don't intersect. So there's an example, and look, you've got to practice these questions. You'll come across a lot of variations, and you need to practice those variations. But this is one way of doing it, and I hope that you work through some further examples. So that's the end of vectors and lines. It's a small subtopic of this topic 2 in Unit 3 of Specialist Maths, but I think it's a pretty tough one compared to some of the others, and there is a lot of variance, so you're going to have to go and practice and then continue to practice up until whichever exam you're practicing for. So all the best, and make sure that you ask any questions that you have.